Good day, everybody. We are here to pass some knowledge across concerning applied regression analysis. Specifically, we'll be talking about the last outline on the course, Start 322. We'll be talking about the last outline on the course, which is multicollinearity. Before we start today, I would like to let you students be aware that this media, in addition to what we have discussed in class on multicollinearity, it's basically meant to pass knowledge across. This media is basically for learning, and it should not be used for any other thing contrary to that on social media or any other platform. And I will advise the rep to see how we could get this across to all other students. This is a value added learning means to what we have discussed in class as far as multicollinearity is concerned. So let's start right away. We'll be talking about multicollinearity diagnoses and solutions, and we're going to be making use of the MS Excel analysis toolpak for our analysis. And in this very class, we're going to learn what is multicollinearity, the causes of multicollinearity, what are the symptoms or how can we detect multicollinearity, solution to multicollinearity, and we are going to make use of a live data to apply live data to actually demonstrate this problem of multicollinearity and how it can be solved. So to start with, what is collinearity? We'll say collinearity is when we have two predictor variables, or what is also called independent variable, in a regression model, and they are highly correlated. And this brought about this independent variable providing redundant information about our y. So we are having two independent variables in our regression model, and they are highly correlated, and they are providing redundant information concerning our y. So we say this is a collinearity problem. It becomes a multicollinearity when the correlation of the independent variable are more than two. So when we have a regression model, and in the regression model two of the independent variable are correlated, we say collinearity. And when we have a regression model but we have more than two of the independent variable being correlated, we say we are having a multicollinearity. And we should recall that basically in a regression model, our x variable is assumed to be independent. You know, we always call it in x independent variable, and because they are independent, we expect them to provide a unique information about how they affect y. That means each of the independent variable, probably say x1, should be able to provide a unique information of how it affects y. Say x2 should be able to provide its own unique information how it affects y. So it's a background knowledge of a regression model, but this is what we should have as a background knowledge about a regression model, and see how collinearity actually affects this as we continue. So when we have all these independent variables expected to be assumed and to be able to provide unique information, so this unique information is also demonstrated in the information matrix. Probably when we are having a multiple linear regression, the information matrix is expected to provide a unique solution of our OLS estimate. That means the OLS estimate for each of the x should be unique. So when uniqueness of x is affected by multicollinearity, what do we have? The basic knowledge, our y is expected to be independent. They're expected to provide unique information about how they affect our y. But when this uniqueness is affected by multicollinearity, what are known depending on the variables of interest to us, then this is our error term. So when we have our model, a regression model of this nature, we can definitely start making inference in this manner. We can say our B1 is a change in y for 1 unit change in x1, y x2 and x3 is held constant. We can also deduce this also for beta 2, that beta 2, which is the coefficient for x2, implies that the change in y for 1 unit change in x2, while our x1 and x3 is held constant. Also, we can also have this for beta 3 as the change in y for 1 unit of change in x3, while x1 and x2 is held constant. If you look at this, you can see that, for example, for this b3, we say our x1 and x2 is held constant. That means they are fixed, which shows in us trying to relate this b3 to how it change y for 1 unit of x3, x1, x2 are not to interfere in what is happening between x3 and the y. That means they are held constant, they are fixed. The same way, when this coefficient or slope beta 2 is trying to tell us the change that is happening in y for 1 unit change in x2, you can see that we are talking about x1 and x3 has nothing to do with the process. They are held constant, they are fixed. This is a proper inference for our regression model, and this is what we expect to have. But when we have the problem of multicollinearity, in a case where probably this x1, which is uniquely trying to explain this y, is correlated between, there's correlation between it and any of x1 or x2, probably it might even be correlated with both of them at the same time. Then there becomes a problem. That means in us trying to make inference of this slope, there will be interference of either of x2 or x3. We could even have interference of both of x2 and x3, depending on what has happened between x1 and these remaining two variables. So this form of inference becomes difficult. So the uniqueness of x is being affected by a multicollinearity problem. So what do we have? We can no longer say our beta 1, is change in y for 1 unit change in x1, y x2 and x3 is held constant. This is no longer possible. The same thing for beta 2. We can no longer say our beta 2 is change in y for 1 unit change in x2, y x1 and x3 is held constant. This is no longer possible because of the presence of collinearity. So what do we do? Mathematically also, our whole estimate which is being derived by looking for estimate where the error is minimum. That's the principle of the OLS estimate. And how do we derive? We derive it by partial derivation of our sum of square error based on the independent nature of x. So what are we talking about? This is still the form of regression model we talk about in question 1. We want to make our error term the subject of the formula. So when we make our error term the subject of the formula, we have this. If we are dealing with the method and matrix, we have this. But algebra, which we'll be interested in now, we're going to have this equation 4. So this is our error term being squared. So we square both sides. So we are talking about the sum of squared error. So this sum of squared error in the OLS method for estimation for a regression model, it's having the partial derivation of this sum of square error with respect with the parameters that is of interest per time. That means when we are interested in estimating beta 1, which is the parameter or coefficient for independent variable x1, we differentiate sum of square error with respect to beta 1, while these other ones are being held constant. That means everything that has to do with x2 is held constant, everything that has with the x3 is held constant, but we differentiate with respect to beta 1. So this beta 1 is uniquely expressing the effect of x1. When it comes to the turn of beta 2, we are going to do a partial differentiation of this sum of square root with respect to beta 2, while all this one is being held constant, this is being held constant, being fixed. So this will be the uniquely estimated parameters. The same thing for beta 3. So this estimation is based on the assumption of the independence of these variables. But in practice, when they are not independent, it actually is going to affect the estimate we are going to have. The reliability of our estimate will be questionable. So let's continue as we see some of those things. So this is what we are talking about, the partial derivation of sum of square error with the respect to beta that is of interest per time. So bi, so when I is 1, when I is 2, on and on, depending on the number of variables that is of interest in the work. So let's continue. What are the causes of multicollinearity? Inaccurate use of dummy variables can lead to multicollinearity. Repetition of some related factors can also lead to multicollinearity. So what are we talking about? For example, in a particular regression model, we have year of education and we have income also dealing as a variable. Theoretically, you see that years of education and income might actually be providing the same effect on y, because normally any person with year of education, depends on if you have a master, your year education is expected to be more than somebody with a secondary school leaver. And it's expected that somebody with a master in a public service is going to earn more than somebody with secondary school certificate. So, which shows that when you check their income, you always find the income of somebody with a master higher than somebody with secondary school certificate. So, invariably, these two variables might actually be expressing the same factor. Also, height and weight, for example, you find out that not in all cases, but in most cases, persons with the highest height, it's likely to weigh more than person with the lowest height in most cases. So you find out that height and weight theoretically could also be expressing the same factor. They are related factor. So when you have this mixed up in your model, you are likely to have a problem of multicollinearity. Also, poor design of experiment. In any experimental design, if the design is not well laid out, you are also going to have a problem of multicollinearity. So we also have what we call structural multicollinearity. This is because when you create new predictor variables, for example, you already have a model and you are using in your model, you try to create a new predictor variable. This can also lead to structural multicollinearity due to how you structure your independent variable. So the presence of product effect, interaction effect, such as where is required in a polynomial model. So what are we talking about in this case? When we have when we have in a polynomial model, initially we have our x, see this as x1. Okay, let me come here. We have our x1, and from x1 we want to know the product effect of x1. So we now have x1 square. We have x1, the interaction effect between x1 and x2, just as is required in a polynomial model. All this interaction effect, product effect are likely to cause the problem of multicollinearity. Also, the last one here, insufficient data can also cause collinearity. Okay, let's now look at the symptoms of multicollinearity. when you have inflated variance of your slope or your coefficient, and you should know that the square root of this variance is the standard error values for our coefficient. This is what we are talking about. If you check our model in equation 1, these are the coefficients we are talking about. When you estimate their variance, when their variance is inflated, it's a symptom of a multicollinearity problem. When you have a R squared that is large, and your model generally is statistically significant, that means in your F and your ANOVA table, your F calculated is greater than your F tab, and that means your model and your entire model is statistically significant. However, your individual beta under your T calculated or T tab, some of them are not statistically significant. It's a problem. It's a problem. You can see when you are having a model almost able to describe 99% of the data, and you have the individual variables or coefficient of the variables in the model, some of them are not significant. It's a problem. It's a kind of contradiction. So when you have such as this, is a symptoms that there's a problem of multicollinearity. Also, removal or addition of one predictor variable results in large change to the model. When you have your model already, and you've already analyzed, you have the data, you've already analyzed the data, you've already set up your model, and you decide to go over again your data and remove one predictor variable, or you have a new predictor variable and you analyze your data and you set up your model, and the